Large language models are incredible at writing code and understanding language, but when it comes to constrained optimization, they consistently fail. Give a model a scheduling problem with hard precedence rules and soft user preferences, and it will almost always violate a constraint or miss the optimal solution. The issue isn't a lack of training data. It's that LLMs are probabilistic token predictors, not exact reasoners. They simply cannot navigate the combinatorial search space required for multi-constraint optimization. So what if we stop asking the LLM to solve the problem entirely? Instead, we treat it as a semantic translator. The pipeline works like this. You give the model a natural language description of your constraints and preferences. It generates Python code using the PySAT API to formally encode the problem as a weighted partial MaxSAT instance. Hard constraints become mandatory clauses that must be satisfied, while user preferences become weighted soft clauses that the solver minimizes. Then an exact, sound MaxSAT solver like RC2 takes over. It guarantees a feasible, provably optimal solution. But how do you verify the LLM's encoding? We decouple solution validity from encoding correctness. Every generated solution is independently checked against a canonical MaxSAT reference. We verify two things: feasibility, meaning all hard constraints are satisfied, and optimality, meaning the objective cost matches the canonical optimum. This allows multiple valid solutions and different encodings, but ensures every accepted output is mathematically correct. The results are stark. Baselines like direct prompting, chain of thought, and program of thought achieve near-zero acceptance on complex families like maximum independent set and scheduling. The MaxSAT pipeline, however, pushes acceptance rates above 80% for state-of-the-art models. An intermediate planning step helps stronger models structure their encodings, though it can introduce error propagation in smaller models. The takeaway is clear. LLMs shouldn't be trusted to perform optimization reasoning. They excel at capturing human intent and translating it into formal specifications. When you externalize the combinatorial search to a sound symbolic solver, you get a system that's both flexible and rigorously verifiable. If you want reliable, preference-aware decision-making, stop asking the language model to think. Just ask it to code.